many of these little computational units that did this rendering. So somebody or another at some point realized that, oh, we can exploit this parallelism of all these little processing units to actually do computations. So that's the basic idea here. Sometimes you'll see this referred to as, oh, this is a little small, general purpose GPU, so GPU computing to be able to do that. And the basic idea when you're computing with the GPU is we've got all these little processing units at your disposal. So the idea is that it's going to work, the context in which it works is if you want to do the same calculation on lots of pieces of data. So this is basically massively parallel in terms of the data, but you're basically executing the same computation or instruction on all of those pieces of data. Which this also goes by the name of single instruction multiple data, or SIMD. So you could think of all the different sorts of computations that you might do that are sort of massively parallel in this way. If you're doing sort of simulation studies, bootstrapping, random forests, any of those sorts of things would work in this kind of framework. Okay, so you basically need a machine, a computer that has a GPU attached to it. We don't happen to have any of those. There's at least one person here at Biostat. So Biostat, I think, does have a machine with a GPU on it. Is anybody here in econ? No? Okay. If anybody, econometrics also has a GPU. So we're going to do this on an Amazon EC2 virtual machine. And I've basically set up the virtual machine so that it has all of the various software installed such that you can do all of the things that are done in the demo. And the machine image, which is basically the snapshot of an Ubuntu Linux operating system with all of this software installed in it, is available on Amazon. So you could actually start up your own virtual machine using that Amazon machine image that I've created. And in this case, I've actually created a VM from that machine image, and that's what's running right now that we'll do the demo on, and that at least one of you was able to connect to, and one of you was not able to connect to. Okay, so we're going to, there are a few different pieces of software that we're going to use. There's this basic platform called CUDA, which was released by NVIDIA and works on any NVIDIA GPU, which is one of the main, NVIDIA is one of the main suppliers of GPUs. And so I've got this Amazon EC2 virtual machine with an NVIDIA GPU, so we can use CUDA with this GPU. Okay, so in this case, the virtual machine that we're running it's an Amazon instance that's called a G2.2X large. So that's I think it has 8 CPU cores. It has, it might have 2 GPUs on it, I forget. We're only going to use one of them in any event. And the GPU has 1,536 cores on it. So that's sort of the parallelization that it provides. And the GPU itself has 4 gigs of memory on it. So one of the things that we're going to talk about is the fact that you basically need to transfer any data you have from the memory of the CPU to the memory of the GPU. Then you can do your computation on the GPU. The results are going to be sitting on the GPU, and then you need to transfer the results back to the CPU. So that's sort of what I've sort of drawn out here. And then the GPU threads that are doing the computation are then going to access the GPU memory. So that's sort of a flow chart of what's going to have to happen. And the other thing to keep in mind is that transferring data back and forth between CPU and GPU memory is fairly slow. So you generally want to try and make sure you minimize this, and then if you can, you might want to actually generate. If you're doing a simulation study, you might want to generate the data in the GPU memory without ever generating it here, and you want to minimize sort of what output you have to bring back to the CPU. And the other thing that indicates is you don't want to be doing a lot of things where you do one part of your computation, bring the information back to the CPU, then you have to bring it back to the GPU, then do another computation. You want to get everything onto the GPU and hopefully do as many of the steps of your computation as you can on the GPU that just access the GPU memory. And then only at the end of all that, bring everything back, bring the results back to the CPU. So that's the basic workflow. Okay, so I have some information on here. Obviously, this is not slides and is more intended for looking at later on as a tutorial. I have some information on here on how you would go about starting up an Amazon virtual machine using this image that I've created. You can do that with a tool called Star Cluster. or there are other ways to do it, but that's one of the easier ways. Okay, so then I have some instructions that may or may not work for you for actually logging on to this particular virtual machine. Okay, so I'm going to just do that here myself. So I'm going to, oh, I guess I already, let's see now. Okay, so I have, all right, this, let's see, where was this here? Okay. Okay, so there's both an Ubuntu user on this, and I'm actually going to switch over to my own username here. Okay, so all of the materials are in this GitHub repository that I've cloned onto this machine. So these are the various R and Python and CUDA code files. And the other thing I want to do is I want to open up a second terminal onto this machine so that we can do a version of top to see the activity on the machine while we're running stuff. So let's see. Okay, so this is basically a sort of very simplified version of top that's looking to see what's going on in the GPU. So it's doing little snapshots every second. It's showing what's the utilization of the actual GPU in terms of computation and what's the utilization of memory. So obviously I haven't started to run anything right now, so there's nothing going on, but that'll be interesting to look at as we actually run stuff. Okay, so some of the tools that I've got on this loaded onto the VM are CUDA, which is basically this platform for programming on the GPU. And it basically allows you to write C or C++, or I think potentially Fortran code, and basically make calls to do the computation on the GPU. There's a BLAS, the basic linear algebra. There's a BLAS for CUDA that does the underlying linear algebra on the GPU. And there's also a package that's sort of related to CUDA that allows you to do random number generation on the GPU. And then there's both an R and a Python front end to CUDA that will basically allow you to do the computations on the GPU, but do a lot of the pre and post processing on the R or the Python side of things. And then finally, there's a package called Magma. And Magma is basically a package that allows you to do, it's basically the analog to LAPACK for doing matrix factorizations in various high-level matrix algebra and linear algebra. And it basically allows you to do it on both the CPU and the GPU, and my understanding is sometimes it sort of splits up the computation in a hopefully somewhat optimal way between the GPU and the CPU. So that's a package that you can also make use of. And there is an R package called Magma as well that is basically an interface to the base Magma package. Okay, and CUDA is only for these NVIDIA, for that particular hardware maker, for NVIDIA GPUs. So there's also there's sort of an alternative to it called OpenCL that will work on other GPUs as well. We're not going to go over that here, but there's also R and Python interfaces for OpenCL as well. Okay, so any questions so far? Okay, so the basic workflow that you would generally do on a GPU is basically you're going to write a little core function called a kernel that is the core calculations that you want to do. And this kernel function is going to get called for each, it's going to basically get called for each of the individual chunks of data that you want to do the processing on. So each of the individual computations is called a thread. And what you do is you basically, there's sort of a hierarchy of these threads that you specify. And then basically each unit of computation is going to get done as a thread. So I mentioned before on this particular GPU there are 1,536 processing units on the GPU. So the idea is if you really want to maximally exploit the GPU, you want to be having at least thousands and thousands, if not tens of thousands or hundreds of thousands or millions of these individual computations. So you want to be launching a ton of these different threads, say thousands or millions of these threads. And what's going to happen is the underlying, the software is basically going to dispatch these computations to the GPU. So suppose, say, 1500 will start initially. As those finish, another 1500 will start, and it'll basically just cycle through however many of these threads that you specify. So when you specify the threads, you actually specify that you want a block of threads. And that could either be a 1D block of threads, a 2D block of threads, or a 3D block of threads. So you could specify, I want to have blocks of 1,000 threads, or you could specify I want to have blocks of 30 by 30 or 900 threads in a 30 by 30 layout. Or you could specify I want to have a block of threads where the block is a 3D layout, so like 20 by 20 by 20 threads, something like that. And then each of these blocks is itself arranged in a grid of blocks. So if you want to count up the total number of threads for your computation, you need to figure out how many threads are there in each block, and then you need to figure out how many blocks are there within your grid of blocks. And I don't actually know a whole lot about the best way to choose the layout of the blocks and the layout of the threads within the block. That's something, if you got sort of more advanced in this, you could go look and get some more information about that. So we're just going to do something very basic, like we're going to specify that each of our blocks is going to contain something like 1,000 threads, and then we're going to have a grid, say, of 30 by 30 grid of blocks. So that would give us 30 times 30 times 1,000 total threads, if that was how we chose to do the layout.
Just on a high level, is there a reason you want different configurations? Is it like a communication cost thing, or?
Yeah, I mean, one of the things, I put this in a little bit, I put this in a little tiny side thing here because I don't want to focus on it because it's not something that we'll actually tackle here, is the threads that are within a block can actually access memory and coordinate amongst themselves, but the threads in separate blocks cannot coordinate across themselves. So if you were doing more sort of sophisticated coding, instead of just treating this as sort of a huge number of threads that are just massively parallel and don't do any communication, you could set up your computations so that you're doing something within a block for which you need to do some inter-block, within block communication and accessing some memory that's specific to the block. Yeah.
Along the same lines, is there any hierarchy in the compute memory, or is it just flat access time?
Yeah, so I mean, there's this sort of main memory that's going to be accessed by all of our threads, and then my understanding is there's also memory associated with each of the blocks. And then there's probably some sort of specific registers or something associated with each of the threads. So there is a hierarchy. I can't say more about it than that. So our basic mode of operation is just going to be get stuff into the main memory. Each of the threads can access that main memory. And that's going to be where stuff gets stored. So for example, one way that we're going to see in an example here is, suppose we're doing a computation where we have a huge long vector, say millions and millions of entries. And what our computation does is we need to do some computation to each element of that vector. So what we're going to do is we could either, depending on whether we need to create it in advance or we're reading it in from somewhere, we're going to essentially get this long vector into the GPU memory. And then what's going to happen is each of our threads, which I've indicated as this little squiggly line, is going to access the appropriate member of this vector. It's going to get that data. It's going to get that data value, do something with it, and then either in a separate vector or maybe in the same vector, return the result to that entry. So each of these threads is going to be accessing a different piece of this same big long vector that's in the GPU memory. Okay, so threads and grids. So again, this is this idea that we're splitting up the threads into these blocks and then blocks into grids. Okay, let's see. Okay, so another thing that we can do is we can basically query the device to see what basically get some information about the GPU itself. So there's a little utility that I've compiled from code here that if we just run this device query, it'll tell us something about the GPU. So it says, okay, this CUDA capability is basically sort of different releases of the hardware and accompanying software capabilities of the GPU. We're going to generally be relying on having the CUDA capability of 2.0 or greater, and that will allow us to do certain things like working with double precision floating points as opposed to single precision floating points. So originally these GPUs were just designed for doing single precision floating point operations. This tells us that there's 4 gigs of RAM on the GPU itself, so that's going to be useful to know in terms of how much data we can actually have in memory on the GPU. This tells us about the cores. There's a whole bunch more stuff here that is more complicated than I understand about sort of the layout of all these threads and whatnot. But a couple of things to note here. It says the maximum number of threads per block is 1024, so that's the maximum number of threads we can have in a block as I've represented it here. And it also says the maximum dimension size in any, so you can have up to 3 dimensions. You can lay out your threads in up to 3 dimensions within the block, and you could at most have 1024 in the first dimension, at most 1024 in the second, and at most 64 in the third. You can't obviously have this by this by this, because that would then exceed the maximum of 1024 overall. And then this line here tells us what's the maximum number of these blocks that we can lay out in this arrangement of blocks of threads. And so that's the maximum is this many in the x dimension, this many in y, and this many in z. So our basic approach for these demonstrations is we're going to use 1,024 threads within a block, and then we're always going to use one. We're not going to use the third dimension of the grid, and we're then going to choose the first and second dimensions just so that we have enough threads in total to do the number of computations that we want to do. So we're basically going to say we want to make sure that 1024 times whatever we put here times whatever we put there multiplies up to be more than the number of computations that we want to do in parallel, and that will ensure we have enough threads to do all these computations. Okay, any questions about that? All right, so let me see where I am here. Okay, so I sort of said this already. The basic mode of operation is we're going to allocate memory on the GPU, transfer data from the CPU to the GPU memory, launch a kernel to do our computations. We might then go on and launch another kernel, maybe a third kernel, however many kernels we want to launch, do whatever computations we need to do, and then we're going to transfer the results back to the CPU. And in some cases, some of this transferring of data ends up getting hidden from you by some software layers that are in between you and the actual computations, and in other cases, we're just going to manually do the transferring back and forth. Okay, so the other thing that we're going to need to do in our, well, let me just go to the example and this will become clear. So let's just do a very simple example where we basically have each thread split out a message that just says, hello, I'm a thread and I'm reporting for duty. So we're going to write a piece of code. It's in this hello world.cu file, and then we're going to compile that code with a line that looks like this. So this NVCC is the analog to GCC for doing the compilation of the CUDA code. This is the input file. This is basically these are basically some flags specifying that we want to make sure and use the one of the more recent compute capabilities of the GPU. And then this is just going to be the output executable file. Okay, so I'm going to go ahead. Let me make sure I'm okay. So I have the hello world.cu file here. I actually have the executable already, but we'll just compile it again just for fun. So that should return, and now I'm just going to run the executable.
Should we just clone into our personal folders? Or?
Yeah, you can do that. Yeah. Okay, so let's actually, before we run it, let's actually look at the code. So this is just the code sitting on it in the GitHub repository. So what does the code look like? Well, it has some header. It has to reference some header files that are part of this CUDA platform. And I'm going to define some constants here. These are going to define my block of threads and my grid of blocks. So in this case, I'm saying I'm going to have each block is going to be a 512 by 1 by 1 set of threads. And then I'm going to have a 20 by 2 grid of blocks. So I'm going to have 40 times 512 separate threads here. So about 20,000 separate threads. And then the key is to write a function that is the kernel function that is the function that's going to get used on in each of the threads. So it has a form that looks like this. You can pass in arguments. You use this global syntax. And then what this does is this block IDX and block dimension and thread IDX and is there anything else in here? These objects are basically available to your kernel, and they're basically you're basically going to write a little bit of code that just does the arithmetic of figuring out what's a unique thread ID such that I can uniquely identify any one of my threads here. Okay, and that's, for example, what's going to get used to determine which element of the vector I want to get access into. So this is all about basically figuring out a unique index for this particular thread. And the reason is this is going to get run identically on each of the, this same code is going to get run identically for each thread, and we want a way to be able to identify threads from each other. So this is basically just the arithmetic of determining an index value that's going to be unique for each of the threads. And then, and so the block dimension basically just says what's the dimension, the 512 by 1 by 1 that I chose. The grid dimension says what's the dimension of these blocks, which I said was going to be, in this case, was 20 by 2 by 1. And then the thread index is basically a unique index associated within each of the thread blocks. So then I need to get a unique index across all of these blocks, and that's what I'm doing with this calculation here. So all this is going to do is it's just going to go ahead and print out hello, and it's going to identify that it's thread number whatever out of the total number of threads, and it's going to identify where it's located within the block and which grid, which block it's located within the grid of blocks. So that's all the kernel does, and then the main function for this program is very simple. It just says, okay, there's this structure that contains the three-dimensional information about the block size and the grid size. This is the 512 by 1 by 1 and the 20 by 2 by 1. And then the total number of threads is just going to be the multiplication out of those sizes up there. And in this case, I have a little check in here to make sure that the number of computations I want to do is not more than the number of threads that I'm creating. So I want to make sure I have enough threads to do all of my individual computations. And then the way that I launch this kernel and run this kernel is I give it the name of the kernel, which you may have noticed up at the top was called hello. I pass in the grid size and the block size information in this triple arrow notation. And then if I had any arguments to the function, I would pass them in here. But in this case, I didn't have any input arguments. So that's going to go ahead and just basically spawn all of these threads that then go and do the computations. And at the end, I have this synchronize. And what the synchronize basically does is say, wait at this point in the program, wait until all of the threads have completed, and then you can continue on. And the basic reason for doing that in this case is because I need to do that in order to actually have the print statements actually go ahead and print out to the screen. If not, they get sort of held in a buffer and they never get printed out. Okay, so now if I just run this, we'll see that it's indeed printing out all this information about the threads. See if I can get up towards the top. I guess it would have been easier to do this. Okay, so it says, okay, my block index is 30, so I'm the 30 block, so this block down here, out of my 20 by 2 grid of blocks. And I'm thread number 448,00, so I'm one of this, say I'm this particular thread within the block. And my unique thread index amongst all of the threads is, in this case, 1984. And so you have no guarantee that these are not going necessarily getting printed out or even getting computed in any particular order. So in this case, the first one that happened to print out was this 1984 one. And so this just shows that it's that each of these is getting that we're getting threads from different blocks, and we're just sort of cycling through, and it's doing the computation on all of the different threads. Okay, any other questions at this point?
Did you run something after that NVCC thing? Sorry.
Did I run anything after it?
Did all of that just happen by running that?
No, the NVCC compiles it.
Yeah.
And then I just ran hello world. I just
Oh.
ran the executable. Yeah. Okay. So the next thing is, okay, let's actually do a quote-unquote real example. So the thing that I'm going to do here is I'm basically just going to do a normal probability density calculation on a very long vector of numbers. So it's, you know, obviously a silly calculation, but you know, you could think of a real example where you have, you know, a very, very large data set. You have IID data, but the likelihood function is expensive to calculate, and so you want to farm out the calculation of the likelihood function and do it in a massively parallel fashion. So that's sort of what we're mimicking here. Okay, so now I have this CUDA code file kernel example.cu, and we can go ahead and take a look at what that looks like. Okay, so again, I write out my function that is the CUDA kernel. I have the same sort of code up here that creates the index that's going to uniquely identify each of the threads. Okay. And now what does this do? Well, this says, okay, if the index is less than the total number of computations I want to do, then go ahead and do something. Otherwise, this thread is basically just going to exit without doing anything. So I might create, say, 5,020,000 threads, but I'd only need 4,900,000 threads to actually do the computation, so some of them don't actually get used. And okay, so then I say, okay, this is just the normal probability density function. The only really interesting thing here is I'm passing in mu and sigma. I'm passing in the total number of data points, the total number of values on which I'm doing the likelihood calculation. And I'm passing in a pointer to this very long vector of values. And what's going to happen is, based on the index value that this thread calculates for itself, it's going to go in and grab the value from this long vector of doubles. It's going to do the computation, and then it's going to put the value back, the resulting density value, back into that same vector. So it's just going to basically, you know, if it decides that it's the fifth thread, it's going to pull that value out, do something, and put a value back in the fifth position. So this vals object is shared across all of the threads, and it's just sitting in the GPU memory. And then I wrote a little function that will just do this on the CPU as well, and that's just so we can do a little bit of a speed comparison. And there are a couple little helper functions, but the main part here, here's the main function. I have a pointer to an array of doubles, CPU vals, a pointer to an array of doubles, but this is going to be basically a reference to the GPU memory. And then I have a little for loop so that I can do my computation for different sizes of this vector. So I'm going to cycle from, you know, for a fairly small calculation with 32,000 observations up to one that has, whatever this is, 134 million calculations. So in this case, I'm just doing a simple allocation of memory for the values in the CPU memory. And then I do an analogous allocation of memory on the GPU, and that uses this CUDA malloc function, which is part of the CUDA platform.
Wait, so are you allocating both of these memories from the thread that you're in?
No. This is right. So good question. So let's make sure we know where we are here. So this is the main function of the program.
So if you actually wanted to like not overwrite what you already had and you wanted to like take some new memory or something, would it be better to allocate that in advance and then send it in and say, oh, this is where you can write?
No, it would be better to just allocate it in the GPU memory, because you don't want to be transferring stuff from the CPU to the GPU unless you have to.
Oh, I guess I mean while you're in a thread, like so for instance in the calculation that you
No, in general you would allocate the storage in advance on the GPU from the main function.
And then you would send like to your particular thread. So for instance, instead of overwriting that vals thing, you would say, oh, okay, here's where you're supposed to write.
Yeah, that might have been a better example. I would have double vals, and then I would double star vals, and I would also have double star output.
Okay.
Yeah.
Can you do memory allocation inside of threads?
You know, I'm sure you can, because there's this. I would guess that you can, because this idea that you have this little bit of memory that you can use access just from the block.
And you can
but it would be local.
That. It's not just a cache bit. I mean, it's not like, you know, an L2 cache in the processor.
Yeah, I think you can, although I didn't look into this, so I don't actually know how you would do it, which is why I'm being hesitant as I answer. Yeah.
So when you write to vals there, Is there any sort of locking that you ever need to do, or is it all just
The locking is inherent in the fact that I've got the index is unique to the thread.
Yeah.
But no, otherwise there's no locking, and I could have written this in a buggy fashion so that two threads were trying to write to the same place. Yeah.
So what happens if you do that? And do you experience slowdowns if you have a bunch of threads trying to move from the same?
Well, I mean, it would be a bug in the sense that presumably you don't want to be overwriting values because you don't know what order all this is going to be happening in. And I don't know whether it would be a bug in the sense it would crash or it would just be a bug in the sense that you'd get back nonsense results.
But maybe like if two threads were just trying to read the same thing and not write it.
Right, that's a good point. I think that's probably fine. I don't know whether you might end up with competitions such that they would sort of conflict with each other or not. My guess is not, but I'm not sure.
Okay.
Okay, so back to our main function. So I've allocated memory. In this case, I'm going to dynamically determine, I'm pre-specifying there are 1024 block threads within a block. But based on the size of my computation, I'm going to dynamically determine how many of these blocks I need. And that's what this, that's what this computation does here, is it just does some ceiling and square root calculations to figure that out. So I set up the block size and I set up the grid size. This I did in advance. This I'm doing dynamically. Again, I have my check to make sure that I have enough threads for the number of computations. I'm going to call a function that just fills in values into the vector in the CPU. This is just basically me simulating data, just so I have something to work with in this case. And now here's sort of the more of the guts of it. I'm going to do a memory copy from the CPU memory to the GPU memory. So that's what this CUDA mem copy does, and I have to tell it how much memory I'm copying, and I have to tell it I'm copying from the host to the device. So the host is the CPU, the device is the GPU. I have a check here. CUDA has a number of different special sort of variable types, which I think this is one of them. Yeah, this CUDA stat is defined to be of the CUDA error T type, and I can check. Oops. Damn it. I can basically check whether there was an error returned from having done some of these by having it return this and then checking. Then I do a synchronize. This is again because I'm doing some timing here, and I want to make sure that I get the timing specific to the actual piece of the computation that I'm trying to time. And here I'm just doing some stuff to try and keep track of how much time it takes to do each of these pieces. And so then I actually call the kernel. This is the name of my kernel. Again, this is the grid and the block information. In this case, I am passing arguments in, so that's what that is. And I'm passing in a reference to the GPU memory that's going to be accessed by each of the threads. Again, I do a device synchronize to make sure that this timing statement only occurs after all of these threads have finished their computation. And then I copy from the device back to the host with another memory copy. Down here I have the calculation where I do the analogous computation on the CPU just for comparison. And then I print out some of the timing information. So any questions about this before we actually run it? Okay, so the
Does anything weird happen if you and I run at exactly the same moment?
oh, right, because we're all sharing the same VM. I don't know, we could try it and see if we're really brave. All right, so I'm going to compile this. The kernel example, same compilation statement as we had for the Hello World statement, Hello World program. And now I'm going to run it. We might be able to catch it here and see. Oh, yep. So you can see it's showing some use of the GPU. It looks like it disappeared. But at some point or another, this was showing something other than 0. And so we can get some sense of the timing here. So let's look at this. So this is the largest. I did this calculation. I started with the data size of 32,000, and I worked my way up to 134 million or whatever it was. So this is the biggest of them, the 134 million. I calculated that I needed a grid of 363 by 363 times the 1,024 threads per block to get enough threads to be able to do this many all in parallel, although not all in parallel simultaneously because I only have the 1536 actual cores on the GPU. And what does it say for timing? It says, okay, it took 0.3 seconds to transfer the object, the data object, the input data object to the GPU. It took 0.11 seconds to actually do the likelihood calculation. It took 0.04 seconds to transfer it back. Sometimes I'm not totally sure why these take different amounts of time, and it's not always in the same order of which takes longer, so I'm a little bit confused about that. And if we just did this on the CPU on a single core on the CPU, it takes 4.5 seconds. So if we're just comparing computation time, we have about a 40-fold speed up by using the GPU when we have the data size being this big. But if we factor in the transfer, it's not quite as impressive a speed up. So that sort of hits home on this idea that we want to limit the amount of transfer we have going back and forth between the GPU and the CPU. I don't think I have too much more to say about this. This is a little bit unfair to the CPU because I could have written the CPU code such that I distributed the CPU job across multiple cores because this is a multi-core machine. So in some ways it's a little bit unfair. But and you can see we're getting the same results back from the GPU. I just outputted the first 3 normal likelihood values from the CPU and from the CPU calculation and from doing the calculation on the GPU, and they're the same. Although I should have printed out more digits to verify that I'm actually getting double precision on the GPU and not just single precision on the GPU.
Can you run it again just to see what the timing is?
Doesn't
Yeah.
change too much the last 3 times I ran it. At least all mine
Of course, I'm now forgotten what the timing was the first time around. So we had about 0.3, 0.1, and 0.04, and 4.5. And we get, yeah, again, 0.3, 0.1, 0.04, about 4.5. So it's fairly consistent. Okay, so that's, okay, so I'll go through this one more briefly because we're getting lower on time. This example is basically the same example, except you can basically set up the memory on the CPU such that there are sort of 2 ways of doing this. One way is setting up the memory on the CPU so that it's sort of specifically targeted as being memory that the GPU that is going to be used to transfer back and forth to the GPU, and that allows for some speed up in the transfer. And you can also, that's called pinned memory, because the memory on the CPU is sort of pinned in the sense of being sort of specifically designed to be accessed by the GPU. You can also do pinned, and I think it's called mapped memory, where the GPU is actually accessing the memory on the CPU. And both of those strategies can sometimes improve the timing of doing this transfer back and forth. So I haven't played around with this too much, but this shows how you would do that. You basically allocate memory on the host, where it's basically mapped to the device. And then what you can do is then you can basically have this double star GPU values. You can basically have that pointer basically be a reference to this memory that's actually on the CPU. And this function, this CUDA function, is the one that sort of does this association between the pointer that is sort of referencing the stuff on the CPU and the actual memory. And so in the tutorial here, I have some results that show that this in this case does speed up the transfer. Okay, so let me show you how to call CUDA kernels from R and from Python quickly. Okay, so any questions before I move to that? Okay, so basically calling this stuff from R or from Python is going to be pretty straightforward. You still have to write the kernel function, the actual CUDA code that does the kernel calculation. But then all of that stuff where we were allocating memory and transferring stuff back and forth is going to be done in either R or in Python. And to do the compilation, we're going to have to compile it into an output format that's basically short of machine code, and that's what this PTX does. So we can either compile our kernel code, or this file is just going to have the kernel function and not the main function, because R is just going to use the kernel function. We can either compile this from the command line of the operating system and tell it to output this PTX file that we're going to load into R, or in R there's actually an NVCC function that will do this for us. So this is the R CUDA package which Duncan Temple Lang at Davis created. And it's actually still on GitHub. It doesn't actually exist on CRAN yet. So this is actually the R code. So we're going to load the rCUDA package. There's a little bit of sort of preparatory setup. This is going to do the compilation with the appropriate flags and create the PTX file. We're going to load that PTX file into R, and then we're going to just create a simple name for the function by getting the calculate log-like function from this module that we've loaded in. And then I'm going to do the same computation, the normal likelihood computation for that big vector in R, from R, that I did just using the CUDA code. And so a lot of this is just analogous to what we had in terms of the CUDA code, which is I'm setting up the threads and the blocks and the grid as vectors of numbers in R. And then to actually run the kernel, well, I have to do a little before that. I'm going to create this vector in R. So this is an R vector X. I'm going to copy it to the GPU, and there's going to be a little reference to it that's called DX. So that's going to be sort of a reference to the object sitting in the GPU memory. And then I'm going to call my calculog-like kernel by using the .CUDA function, which is basically the analog to .c or .call. If you were calling C code from R, this is just calling CUDA code from R. And I'm going to pass in, okay, I'm telling it use dx, which is this reference to the GPU memory, the vector in GPU memory, but also send in n and mu and sigma. I have to tell it the grid and the block dimensions, just like I had to tell it when I was running CUDA code. And in this case, I have to specifically say I want to work with doubles as double precision floating points. And then I'm going to copy stuff back from the GPU back to R. So this is I'm copying from this dx, the GPU object, back into an R object called out. So that's basically all there is to it. I've got some stuff that I put in here for doing the timing. It turns out you can avoid having to explicitly do the copying back and forth by using a little bit different syntax in the when I use the .CUDA function, and I can tell it that the x that I want as the first argument is actually my R object x, and then I can tell it return as an output that same object. In this case, I'm overwriting the memory that I used for the inputs. So if I do this, I can now start up R, and I can source that rCUDA example. And it'll just run through the code, and we can see what the timing is of that. Or we could just look at what I got before. Okay, so this was the timing that I got when I ran it, whenever it was, yesterday or something like that. So in this case, it took about 0.3 seconds to transfer it to the GPU. It took about 0.08 seconds, so actually less than when we just were calling the CUDA code from CUDA. I'm not sure why that would be in this case. For some reason, it took longer to transfer it back than it did before. So this was basically full time for the GPU calculation. And then if we do the calculation just in R, it took about 10 seconds. If you remember, it took, I think, like 4 or 5 seconds when we did it using basically C code to do the computation. So that's the story there. One of the things to be really careful about is you need to make sure that you get your types in R to match the types that the CUDA kernel is expecting. So our CUDA kernel is expecting that mu and sigma are going to be doubles, and that n, the number of elements, is going to be an integer. So I was very careful in here to, well, I don't need to do anything with mu and sigma because they're naturally going to be numerics in R and therefore going to be doubles. But I was very careful to make sure that I have L here to make sure that this is an integer, so that these threads and the block dimensions are all integers. And I was also careful to make sure that n is also explicitly an integer. And if you don't do that, you can get these errors that are very hard to decipher, as I found out. So that's one thing to keep track of, is that you want to make sure the types here in R match the types that the CUDA code is expecting as an input. Okay, questions about that? All right, so that was doing it from R. We can also do it from Python, and it doesn't look too different. It's actually a little bit easier. We can import some of the necessary Python modules. Turns out in Python we can actually write the CUDA code in just as a triple quoted string here in our Python file. And so this is just the same kernel code. Remember the global and the name and all this business is just written right into the file here. And so I can just call this source module function, and that will basically do all the compilation and the loading it into Python. And then I'm going to create just a name for the kernel function that's just now basically you can treat as a Python function. Again, I'm pretty careful about defining exactly the types that I'm going to use, that I'm going to pass to the kernel. I'm going to generate some fake data in this case. I've got some timing code in here, but then this is really just, I don't even need to do the transfer explicitly myself. All I need to do is call my denorm function. There's a little bit of sort of wrapper code to make sure that I can pass the inputs in and get the outputs back. And then I've got my other arguments, and again, the block dimensions and the grid dimensions. So this is not so different than what the R interface looked like, and even in some ways not so different than what the CUDA code itself looked like when I was doing all of this within CUDA. Okay, so questions about that? All right, well, why don't I do one more thing with random number generation, and then we'll break, and if people want to stick around, I can show you a little bit about linear algebra on the GPU, and if you want to take off before that, then that's fine too. I'll make one brief mention, which is you can use this GPU array Python package, and that will basically, what it basically allows you to do is define vectors in Python and basically transfer them to the memory of the GPU, and then you can basically do vectorized functions applied to those vectors. So it's sort of like in R or in NumPy if you're doing vectorized calculations, except in this case it's doing a vectorized calculation on the object sitting on the GPU. So that's what these GPU arrays are. So there's sort of stuff about taking a Python X and making it into a GPU array, dx, that's sitting on the GPU, and then you can do things like apply the exponential function to that, and this is basically just a vectorized calculation that's happening on the GPU. Or I have, I think I have a dot product example. Here's the format where you take one of these GPU arrays that's sitting in GPU memory and do a dot product of a vector and another vector. In this case, it's the same one. I don't think I was getting great speedups from that. Oh, in some cases I was. You can look at the details if you're interested. All right, so let me close by talking about random number generation. I've basically already sort of hit home. Yeah, Ryan.
Can I ask a kind of separate track question?
Sure.
Is there a way to monitor the progress of the GPU threads without doing synchronous? For example, to know whether something is on?
That's a good question. I don't know off the top of my head, but yeah, it would be nice to know. You could tell it was 50% of the way through or something like that. I mean, you could. I guess this didn't work. I was going to say maybe you can put a print statement in that every 1,000 threads, but we don't necessarily know what order they're going to get done in, and I think the print statement's going to get buffered and isn't going to get printed out anyway, so that would.
So it's all on the GPU.
What's that?
It's all in the GPU memory, right?
Yeah.
None of the threads can be directed.
Yeah, I don't know exactly how it's working behind the scenes, but if you call printf within the kernel, that's the kernel's doing the printing, and then somehow it needs to sort of get out to the CPU and be accessible to print it out to the screen. So I don't know exactly how that's working, but that would probably interfere with this. Okay, so a little bit about random number generation. As I said, if we can generate the numbers in the GPU memory instead of, like, if we're generating tons and tons of random numbers, we don't want to be generating them here and then transferring them and then doing the calculation. We want to be doing the generation here if we can. So there's this curand library that we can use. It provides a few different random number generators, including the Mersenne twister, which is the default in R, and is a pretty good quality random number generator. Remember that if that dealing with random numbers in a parallel computing context gets a little bit tricky. So random numbers are generated from basically a deterministic periodic sequence, and the seed determines sort of where in the sequence you're starting off your generation of the random numbers. So what we want to make sure is we've got all of these many threads going on. We don't want that thread and this thread to be using the same random numbers. So the idea is we want to make sure that, say, the first thread starts here, and then the second thread starts here, and the third thread here, and the fourth thread here. And we want to make sure we spread out the random numbers such that they're distinct from thread to thread. So we can do that by basically setting a seed for the overall random number generation, and then making sure that we assign sequence numbers. And the assigning of the sequence numbers is basically assigning sort of the starting places for the individual threads within the random number generation. So I think maybe the best thing is just to do is just look at the code, and we'll see what has to happen here. Okay, so I have a header file that is for curand. I'm going to end up calling, these are 3 different kernel functions, and I'm going to end up calling these from R, so there's no main function in here. So what I have to do is, there are actually 2 important kernel functions in here. One is basically going to set up the random number generator, and then the next one is going to use it. So to set up the random number generator, this is a kernel function. It's going to take in a pointer to this thing called curand state. And what's going to happen is, again, I'm going to identify my index, so my unique ID for that thread. And then I'm going to initialize the random number generator for this particular thread. I'm going to initialize it with the seed, and then the index is basically going to be the sequence that spaces out the random number generation. And then the result is going to get stored in a state variable that's where there's a specific element specific to this index. So basically what I'm doing is I'm initializing the random number generator such that there's a state for every single one of the threads, and I'm going to store that and then make use of that when I'm actually doing the random number generation. So this is just the initialization to set up the state for each of the threads, the state of the random number generator. And then the way you can ignore this middle kernel here, and then the actual rnorm kernel is going to work like this. Again, I figure out my unique index here. In this case, I don't want to be just generating one random number for each of the threads, because it actually takes a fair amount of time and a fair amount of memory to store this state and to be making use of the state. So instead, what I'm going to do is I'm going to generate, say, 1,000 random numbers for each of the threads, and that'll be more efficient. So this num samples is the number of samples I want to generate for each of the threads. So I'm going to start a massive number of threads, and then each of the threads, and then you generate 1,000 random normals in each thread. So this is just the for loop to generate the 1,000. And what am I doing? Well, I'm just calling this curand normal double. That's going to generate a standard normal, and you'll notice I pass in the state of the random number generator. And then it's going to return a value that I'm then going to store in the appropriate place. So basically, in this case, what I'm doing is I'm creating this huge long vector in which I'm going to store my random numbers. But in this case, the first thread is going to access the first chunk of it. The second thread is going to access the second chunk, and so on and so forth. So those are so I basically have 2 kernels here: a setup kernel and then the random number generating kernel. And then the R code looks like this. So it's again compiling the code, loading the functions in. In this case, I'm going to load in both of my kernels as my setup function as my rnorm function. And in this case, I say I want to generate 100 million random normals, but I want to generate 1,000 per thread, so there are only going to be 100,000 individual threads. And then this is basically like we saw before. I need to, although there's the twist of I need to allocate memory for the random number state. And in this case, it's basically the size of 6 doubles. So I'm going to call my setup code with .CUDA. I'm going to allocate memory on the device to store the random numbers, and then I'm going to call the actual random number generator. And if I do the timing on this, I guess I'll just go back to what I actually found before. So the initialization of the random number generators took about 0.1 seconds. Allocation of memory for storing the random numbers took a negligible amount of time. It took me 0.25 seconds to actually generate the 100 million random numbers, and then it took me, if I do actually need to transfer them all back to the CPU, it took me 0.5 seconds to generate this, to send them back to the CPU. And if I just did it all in a single core in R, it would have taken me about 10 seconds. So if I'm just comparing this number to this number, again, it's about a 40-fold speed up. But if I have to factor in the time for transferring, then it's not as effective. Okay. And you could do very similar things if you wanted to call the random number generation from Python or for CUDA. You just need to sort of mix and match some of the different pieces of code that I've already shown you. So I have some stuff about linear algebra. If anybody want to stick around, I'm happy to talk about that. But why don't we take a couple-minute break so that people can leave gracefully if they want to leave, and I'm happy to take other questions as well. Anything else? The other thing is we're paying by the hour, not a huge amount, but we're paying by the hour for this Amazon instance of the GPU. So I'll leave it up for a few days, maybe for another week if people want to play around with it. And after that, I'm going to shut it off. But if you do want to use it again, we have enough funds in the SCF budget that I could start it up again for you, and I could even start up a specific one for you or show you how to do it. So if you wanted to do it, if you wanted to use this down the road, that will definitely be possible.
Also, I think if you have a Mac, then you actually can run this stuff natively for more recent Macs. So you can test it like that. And
Oh, that'd be cool. I should look into that. That hadn't occurred to me, but that's
yeah. I think the twist is that it has to be OpenCL. So these libraries have parallel versions
okay.
for OpenCL, but they're generally the same.
Yeah, I suspect the OpenCL code and the CUDA code probably don't look too different, although I haven't looked into it. Yeah.
Well, that'd be cool to try out.
Yeah, you can prototype whatever it is and then
Yeah.
spend $5 million on Institute.
Yeah.
But they have lots of money.
Yeah, and I don't know in terms of the relative timings here. It might, depending on what you're doing, you might get better or worse speed ups. This gives us, sort of vague indication of what you might see. But I wouldn't hang your hat on exactly the sorts of speed ups I got. So it'd be worth doing some testing.
So are there any restrictions on the sort of stuff that we can run inside of the GPU threads? Like, can we write to files, for instance?
That's a good question. I don't know. I mean, you can obviously do printf, and you can. There are some other things that you can do that sort of get you outside of the GPU. But I didn't look into writing to files or reading from files.
What about
Hopefully, you could read from files in parallel, because that would be powerful instead of having to read it in. If you had tons of data, instead of reading it into the CPU and then transferring, you'd read it onto the GPU. The only problem is the GPU memory is fairly limited, so you're not going to be able to read in all that much.
Yeah, but there's no way to do sort of a direct read from CPU memory from one of the GPU threads.
I've heard that when you do that, basically you don't get any speed up over just doing it CPU. Like the link from GPU to CPU is extremely slow.
Sure. Yeah, but at least it's sort of simplified.
Wait, sorry, what was the difference again?
Communicating
so
in and out.
Internally, it'll just optimize it as a copy from CPU memory to GPU.
Right. I mean, that gets into this pinned and mapped business. That if it's pinned, then basically what's going to happen is you may not explicitly have to say copy from the CPU to the GPU, but that will actually be happening behind the scenes. And if my understanding is if it's pinned and it's mapped, then actually the GPU kernel will actually be accessing the memory on the CPU. And I think either of those, at least in some cases, will speed up the transfers, but exactly how much and which one is best in any particular circumstance, I'm not sure.
And so I guess my other question was for, are there atomic operations in the GPU threads? So I guess the first is, are there sort of normal synchronization primitives? Like, is there a spin lock that will run without having to do the software from inside of the GPU thread? And are there atomic?
Okay, so you're getting a little beyond my technical knowledge. And can you phrase the question a little bit differently in terms of what you're looking for?
Well, I guess when you were sort of giving that example earlier, I was thinking it doesn't really make sense to sort of calculate all the component wise likely you'd want to just keep a spin lock and then synchronize it and add to the single sum over the likelihoods, right?
Right. So yeah, so how you do that sort of reduction of getting sort of taking the full output and then reducing down to the actual summary that you're interested in. Yeah, I think the way you would probably do that is you'd probably within a thread block do the reduction to say sum up over these threads, and then you'd probably just return the result of that from each of the blocks back, and then maybe sum it up on the on the CPU. I imagine, I don't think there's any way to communicate from here to here, so I suspect some of the reduction is going to need to happen at the level of the CPU.
Sure, I mean, you could communicate through the GPU memory in most times.
Oh, that's true. Right. Yeah. So I guess you could. Right. I mean, if you could figure out the locking, then you could, in GPU memory, basically do the summation. And I don't know whether obtaining that lock and doing that involves a lot of time, because then a lot of things are trying to access into a single piece of memory. Or if
I guess atomic writes would be like an atomic like set and check would be useful, right? I don't know if they at the hardware.
Yeah, I'm not sure. Other questions? All right. Did anybody want me to go through the linear algebra stuff, or? Okay. So you can basically do, if you're just doing BLAS type operations, which are basically just the basic vector, matrix computations, then you can do those with CUDA BLAS. If you need to do LAPACK level stuff like matrix factorizations, they're not implemented in the CUDA BLAS, they're implemented in this thing called Magma. So those are basically the packages that we're gonna use. So Magma is basically a drop-in for both the BLAS and LAPACK. And it will carry out linear algebra both on the CPU and on the GPU. And I think it makes some promises about trying to be smart about doing some of the computations on the CPU and some on the GPU, depending on where it would be most efficient to do it. So there's an R package called Magma that's a front end to the underlying underlying Magma library, and it provides the ability to do various arithmetic stuff. Matrix multiplication, backsolve, Cholesky, LU, QR, a few other things. I don't know if SVD is actually one of the things or not. So just as an example to see what the code looks like, it's pretty straightforward. You basically, here I'm creating my R matrix, and then I'm saying, oh, make a Magma version of that. And this MX is the version that I'm going to be able to run the Magma functions, or the R Magma functions on. So here's I'm just going to do a Cholesky and then a backsolve. So I'm also going to create a vector and a Magma version of the vector. And there's this whole business about Magma gives you a GPU interface and a CPU interface. They're both doing the calculations on the GPU. But if you call the GPU interface, it's going to be expecting the objects that you're operating on to already be in the GPU memory. And if you call the CPU interface, it's going to be expecting the objects to be in the CPU memory. And then behind the scenes, it's going to do the transfer to the GPU memory. So the terminology gets a little bit complicated. But in this case, I think if we just do this by default, it's going to be calling this GPU interface. Although, now that I've said all this whole business about the transferring, the R Magma package is going to take care of the transferring anyway. So sort of where in the background this all happens is sort of what I'm sort of talking around here. But then the basic idea is you're just going to call function names that are from the Magma package, but have the same names as functions that you would call in R, and you're going to call them on the Magma versions of the object. So I'm going to do a cross product of my matrix X. That's going to create a positive definite matrix Y that's going to be on the GPU. Then I'm going to do a Cholesky decomposition that's going to create my upper triangular Cholesky factor, again on the GPU, and then I'm going to do a backsolve of that Cholesky factor and my vector that I'd already created. So all of this is happening on the GPU. And in this case, I wasn't getting particularly impressive speedups, so I don't know if this is sort of a general result or if there are ways to do this more effectively. But for example, if I was working with an 8,000 by 8,000 matrix doing this cross product and then the Cholesky and then the backsolve, the time for all of those calculations was taking about 20 seconds on the GPU and about 47 seconds on the CPU. And the thing to remember about this is the for some reason, this virtual machine has 8 cores on the CPU. For some reason, I couldn't figure out why it's only using 2 of those cores. So this is 47 seconds using 2 cores and versus 20 seconds using the entire GPU. When I went ahead and did, and actually ran the same computation using 8 cores on a CPU on one of the SCF machines on my desktop, it was taking 20 seconds on my 8-core machine. So this 20 seconds is very comparable to the time doing it on the GPU. So there would be no reason for me to do this on the GPU if I can just use all 8 cores on my own machine. So I don't know how general that result is, but
You can set an environment variable and it'll make OpenBlast use more threads. Try that.
yeah, no, that wasn't working.
No?
Yeah. So I don't. Yeah, I was setting OMP-num threads, and I don't know why it was using only 2 on that on the virtual machine.
Huh.
Okay, so we can also call CUDA BLAS and Magma directly from within C code. So here I'll show you what that looks like. Okay, so I've got, again, I've got some includes up here. This is what the compilation is now going to look like. So I've got this code file. I need to point it to the header files that are in a CUDA include directory. I need to link to cuBLAS to the object file, and then that's going to be my output file. And what does this look like? Again, I set up the code to sort of do some tests with different sizes of problems. So I'm going to do an allocation of memory on the CPU. That's going to be A and B. These are just pointers to doubles. Again, there's some synchronization steps in here. I'm now going to allocate space on the GPU, and I'm going to call that DA. And there's a whole bit about it, sort of double ED reference and whatnot. So here are these are these pointers to the memory allocated on the GPU. So I'm going to allocate DA and DB. Those are on the device on the GPU. And then I'm going to fill up my matrix B on the CPU, and then I'm going to copy that matrix to the GPU. So that's done with this call to cuBLAS set matrix. So I'm going to copy from the CPU matrix to the GPU matrix, and I need to give it a whole bunch of information about the size of these objects that I'm doing the copying. And then I'm going to do my BLAS call. So those of you who use the actual BLAS functions may remember that, where is it? Oh, here. DGEM is matrix multiply in BLAS terminology, double, precision, general, matrix multiply. So this call looks a lot like a BLAS call. You have to give it all this information about, am I doing transposing, and what are the sizes of all of these different objects, and there's multiplication by a scalar, and then addition, and it handles a sort of more general set of computations involved in matrix multiplication. So you end up having to pass a lot of these arguments. But the key ones here are I'm passing in the first matrix that I'm doing, the 2 matrices that I'm multiplying, and space to store the output. And these are all GPU objects in the GPU memory. And so that's going to create the output in DA, and then I need to copy it back with this cuBLAS get matrix. I'm going to copy it back from DA into the memory that's been allocated on the CPU, which is this double pointer A. And then there's, again, a bunch of synchronizations, and then at the end of the day, I need to free the memory on the CPU, but I also need to free the memory on the GPU as well. So that's what happens there. And let's see what happened when I ran this. So if we look at some of the larger problems. So this was multiplying 2 8,000 by 8,000 matrices. Took about 0.16 seconds to transfer. It took about 12 seconds to do the computation on the GPU, and then about 0.5 seconds to transfer the result back to the CPU. If I just use 1 core on a CPU, that will take 74 seconds on one of the SCF cluster nodes. So this is 74 versus 12 or so is a pretty good speed up. But if I actually use 8 cores on one of the cluster machines or on my own desktop, then it took about 11 seconds. So this 11 seconds is basically the same as the amount of time it took on the GPU. So sort of depending on what GPU hardware you have and what CPU hardware you have, you may or may not have any real speed ups, at least based on this test, from doing the computation on the GPU.
Have you done bigger things with bigger N? Or does it
No, the reason I didn't do things with bigger N was, remember on this particular GPU I only have 4 gigs of RAM, so I couldn't, at some point I got to the point where I was running out of RAM very quickly. Yeah. But yeah, it would be interesting if there were more GPU memory, it'd be interesting to know if we started to see that the GPU is outperforming the CPU, yeah. And then we can also make calls directly to Magma from C code. And so that looks like this. So here I'm now including the Magma header files. And the compilation flags get rather more complicated, in part because if you're using Magma, then you, what was I going to say about that? Oh, because I'm also linking in the actual CPU LAPACK and BLAS here. So there's a whole bunch of flags about linking in the CUDA header files, the Magma header files, the CUDA and CUDA BLAS SO files, and the Magma and the LAPACK and the BLAS SO files. So there's sort of a lot of linking going on here. Okay, and so again, there's sort of some stuff of the CUDA, defining some variables that are of these CUDA types for error checking. And there's also, I also set this up so that I could set up this pinned memory if I wanted to. So in this particular program, I could pass in a flag from when I call the program at the operating system level to say either use or don't use pinned memory. So here I'm allocating the CPU objects. Here I'm allocating pinned memory on the CPU. So these are pointers to memory on the CPU that are going to get accessed from the GPU. So it's either going to do this or it's going to do that. And then I've got memory allocated on the GPU, and in this case I'm calling Magma malloc. So in some of the cases there's going to be an analogous Magma call to some of the cuBLAS calls. So I could either allocate memory with a cuBLAS call on the GPU, or I could allocate it with a Magma call, and I think they're basically doing the same thing. And then there's a Magma set matrix, just like there was a CUDA set matrix. So again, I'm just going to copy from CPU to GPU with this particular set matrix. And now there's a Magma version of the matrix multiply where the arguments look essentially the same as they did before. But now, in addition to doing matrix multiply, which I could have just done with the CUDA BLAS, I'm also now going to be able to do a Cholesky factorization. So the LAPACK name for Cholesky factorization is POTRF. In this case, there's the GPU version of that I'm going to call through Magma. And I'm going to pass in, so I want the lower triangular, this is information about the size of the matrix, and do the computation of the lower triangular factor on the matrix DA that's sitting in GPU memory. And in this case, it's just going to overwrite, it's probably just going to overwrite the lower triangular, it's going to overwrite the input with the output. And then I can do the same sort of thing to get the matrix back. And I could have, I mentioned this idea of CPU interface and GPU interface to the GPU calculation. In this case, I could have called, instead of the GPU interface, I could have called the CPU interface by leaving off the underscore GPU. And in that case, here I referenced the GPU-based object in memory. And here I'm referencing the CPU object in memory. But the calculation is still going to be done on the GPU. It's either, I guess it depends on sort of exactly how this pinning works, whether it's actually going to access the object on the CPU from the GPU, or whether implicitly it's behind the scenes it's going to do a transfer from the CPU memory to the GPU memory. So that's basically the story there. And in this case, let's see what timing I got for this. There's a whole bunch of different things here because I was turning on and off whether I used the pinned memory or not to try and play around with some of that. And it seemed like it seemed to make a difference in this case. It helped to do the pinned memory. So here's the biggest problem I did with the pinned memory. Again, the matrix multiplication on the GPU took about 11 or 12 seconds. If I do it on a single core, it took about 78 seconds on the CPU using the regular BLAS. And then the Cholesky factorization took about 2 seconds on the GPU and about 12 seconds with LAPACK on the CPU. I think this is with a single core. So this is maybe not that impressive a speed up compared to if we're using a multi-core, if we're using a threaded version of LAPACK or the BLAS. And yeah, so I think that's basically all I have to say. So I suspect, oops, how did that happen? I don't know how I lost the, lost the memory of my pages here, but at least based on this testing, I suspect the big speedups are going to come if you're actually doing these highly parallelized kernel computations as opposed to trying to do linear algebra on the GPU. But there might be some cases where you're doing some big kernel you're doing some computation where you farm stuff out to the kernels and you're doing massively parallel computation, and then maybe you've got something sitting on the GPU memory and you need to do some linear algebra, and then maybe after that you're then going to go back and do some more of these kernel operations. Who knows what the iterations in your computation are going to be, in which case it might be helpful to be able to just do the linear algebra on the GPU itself. So that's what I've got. Any other questions?
I'm trying to figure out what sort of statistical problems are like. Most of the stuff is either so big that it can't fit on one machine, or
right.
Everything that we think about now is like that. So.
Yeah, it's sort of interesting to think about, and I haven't. I was sort of musing on the same question, and I hadn't really sort of thought it through all that carefully. But yeah, exactly which problem would this be particularly appropriate for? I think if you were doing a really big simulation where you had to do a lot of computation, but you weren't using a ton of memory, I think this would be quite useful for that. You know, if you did have, if you're doing some computation where it was, there were a huge amount of computations, but you also were dealing with, terabytes or many gigabytes of data, then this probably wouldn't work all that well because of the memory limitations. Although maybe, per Nathan's question, if you could read off disk from the threads, then maybe that would, then you might be able to do something.
Seems like this would sort of the answer.
What's
like
that?
Synchronization is really, really slow currently inside of, so they don't have synchronization primitives, so
Okay.
doing anything like any synchronization inside of the threads is pretty slow from what
Okay.
people
You just looked up just now.
Yeah, yeah.
Okay. Yeah, so I think if you have sort of modest memory or data sizes, but you've just got massively parallel computation, then this would be useful. So I don't know if you may or may not have a bootstrap or a simulation study that's big enough to warrant doing this. I mean, I can imagine there might be a number of times where it would be helpful for that sort of thing.
It's like optimization would be really good, right? Because you're like calculating the gradient over and over the specific point, like gradient.
That's actually the one thing that I know that. So they did that for deep neural network training, and they started using GPUs, and like it sort of like got them a big boost in the performance of this network. I think it was all due to the fact that they could calculate billions of gradients quickly.
Yeah.
So what can you say a little more about what the larger calculation was?
So actually, yeah, I just know from like being by proximity at NIPS. I don't actually know what they did, but I have a feeling it's that they want to do gradient descent to train this neural network to do like image recognition. And so basically they were able to just create larger and larger networks because they were able to calculate more and more gradients in parallel. So whereas previously it would have taken extra machines or lots of time, this way they could just calculate many gradients in parallel.
So do you know how they're using the multiple gradients? Because obviously optimization is just inherently sequential as you're taking the steps. But what's the parallelization in terms of how they?
So I think you get like a gradient per node, right? So each node has a different like activation function, and then.
So are you calculating some overall gradient from these little pieces of the little smaller gradient calculations?
I'm not sure. I don't know if people know more about neural networks than me. But.
Well, I mean, so the application that I saw was like really high dimension optimization. So if you have 100,000 like points, then you're keeping the full gradient, right? And so every iteration you have to calculate a big gradient matrix to take a single step. So
oh, okay. Right.
Then you don't have to like mess with the transfer back from CPU to GPU.
Okay.
Which is one use case.
Right. Okay. That's cool. Yeah.
Well, so another setting is like where you have like additive loss function. This is like where people do stochastic gradients. So rather than computing, so you have like a sum of basically one loss function per data point.
Right.
So then you can parallelize that easily.
Right. That makes sense. Yeah. Cool. Yeah. So if any of you end up doing stuff with GPUs and end up, with a nice practical example or whatever experience you find, I'd be interested in, getting feedback from you, because I sort of got up and running with this to the stage of basically being able to create the VM, get all the software installed, and to be able to do these sort of toy things, but I haven't done any sort of real calculations with it. So.
Thank you.